published, something on a radiative modular inspired seesaw. And I want to discuss how modular symmetries can potentially give rise to hierarchies of fermion masses. So I will focus on these two works, but it's a neat idea that has also been explored by many, many groups. And so the outline is these three parts. I tell you a bit about the modular symmetry. I will tell you then in a second part about the modular symmetry protected seesaw, and final part, these mass hierarchies at higher genus, which is something new. Okay, so the motivation is essentially the flavor puzzle, and also a bit of testability is nice to have. So the flavor puzzle, as you know, is our astonishment when we are confronted with the hierarchical masses of fundamental fermions. Why are they so spread out, so different from the top to the up, top to the electron? Neutrinos are a different kind of puzzle, but also this spread in this logarithmic scale is a mystery. And also, why do we have these particular patterns of fermion mixing? Why so different in the quarks and in the leptons, where in the leptons you have relatively large mixing? The smallest angle in the lepton sector is comparable to the largest angle of the quark sector. And in the quark sector, in fact, you have a almost identity CKM matrix. So this we would like to understand if this can be derived from first principles, if nature is sending us some kind of message with these structures that we see at low energy. So we search for an organizing principle, and this is where symmetries will play a role. Okay, before going to symmetries, let me just discuss a bit about neutrinos. And neutrinos are particularly light. We know we have upper bounds on their mass, on the mass scale, and we have very nice mechanisms to understand how such light neutrino masses can arise. The simplest one is the type 1 seesaw, where you have a tree-level diagram mediating the 5-dimensional Weinberg operator. And here, this is the master formula of the type 1 seesaw. So let me spend some words on the seesaw mechanism. And if we think about this seesaw formula as numbers, we essentially are on this. I don't know if you can see my mouse.
Yes.
We are on this. Okay, yes. We are on this line that is called unprotected. So essentially, if you are in this scenario, which is just using this, looking at this formula and thinking of these YD/MR as numbers, you either have order 1 Yukawas, but then you are in this corner where the mass that you need for the right-handed, for the new degrees of freedom is very heavy, close to the gut scale, so that you can get light neutrinos. Instead, if you want to do something at low scale, so have new heavy neutral leptons accessible at your collider, the problem is that you have to reduce MR while reducing also Y. And so you have small couplings. You are in the other corner. So this is bad because you cannot test it. The region that is collider testable is when you could, if you could have large couplings and at the same time a small Majorana mass for the right-handed neutrinos. This can happen actually because these are not numbers. This is a matrix product. So you could have some cancellations driven by some lepton number symmetry. And in this kind of symmetry protected scenarios, we can really be in this corner where you have light enough, you allow for light enough states that are testable at colliders because also they have large enough couplings. So this is the first, just to continue the motivation, something that modular symmetries we will see can give us, but it's a more general statement, is that you can, if you have a approximately conserved lepton number symmetry, you can lower the scale of the new states and have sufficiently large couplings so that you can detect these guys at colliders. If the L symmetry is exact, you would have something like here Dirac state, okay, of heavy Dirac state, and massless Majorana, sorry, file, essentially massless neutrinos. Of course, we need neutrinos, like neutrinos, to be massive, so we have to turn on some epsilon, some small breaking of lepton number, and then you will have like neutrino masses, which are Majorana, and the heavy states become pseudo-Dirac. So they are Majorana, but they will appear very Dirac, apart from a small splitting among them. And this, as Antush and Fischer wrote in this paper, you can essentially, in the limit of L conservation, you can think of your mass metrics of the type 1 seesaw as something like this. So you have, okay, this block you cannot fill in. Then you have some zeros forced by lepton number, and no light neutrinos are massive. If you turn on a small breaking of lepton number, it depends on where you do it. If you do it in the Dirac type structures, so in these off-diagonal blocks, you are doing something like a linear seesaw. So if epsilon goes to 0, you don't have mass, you don't have neutrino masses. You need epsilon different from 0, and you have essentially epsilon suppressing your naive expectation. So you can put some suppression in the usual seesaw part, but you also can use epsilon for some suppression. Basically also in these kinds of linear scenarios, the heavy states will split, but they will split very little of the order of the neutrino masses themselves, like neutrino masses. If instead you perturb the bottom right block also, you are doing something also of the kind of an inverse seesaw. And here, again, the light neutrino masses will be seesaw times a suppression. So you don't need to suppress everything with the seesaw. You could, in this way, go away from the seesaw limit. And of course, since you are now directly hitting this block, or Majorana block, your splitting will generically be order epsilon. Okay, so this is basically the motivation. We want to see, just going back a bit, we want to see if we could find some framework where we can address the flavor puzzle, CP violation, testable mechanism for neutrino masses, and the hierarchies of the flavor puzzle. I'm repeating myself. Okay, any questions so far? If not, I will tell you a bit about this modular framework. Okay, so the modular framework, the idea is to generalize the typical approach of flavor symmetries, which will connect different generations of fermions orthogonally to GATs, which connect different kinds of fermions within the same generation. The traditional approach is based on non-abelian discrete flavor symmetries, because you can have these multiplets where you fit the generations, and you can use them to have some predictivity on the mixing. However, there are some problems, and these problems with traditional flavor model building based on these groups have motivated the modular approach. One problem is that you need to always break this non-abelian discrete flavor symmetry. So you need to invoke a scalar sector which does this job. Typically, these flavons are scalars with which are not just one, they are many. They fill in triplets, doublets, etc. of this finite group, and you are left with troublesome scalar potentials, which you may need to shape and drive to your desired minimum. And also you have some lack of control over higher dimensional operators. So the idea of Ferulio was to invert a bit this logic, and instead of starting from a nice symmetry group which we like and deriving from that the symmetry breaking sector, why not do the opposite? Start from a very small or very simple symmetry breaking sector and see what kind of groups and representations you can make compatible with it. So the idea of modular symmetry is indeed to improve on this paradigm. It will be able to constrain more things than the typical approach because it really shapes the mass matrices. We will see that, unfortunately, it requires a bit of extra things, which is the MSSM in the minimal setup. And the supersymmetry is required, and because of holomorphicity. We will see this in a moment, why it's clearly a requirement. And there, of course, have been some attempts to go beyond it. But once you accept that, the point is that you can just use one field, a complex scalar called the modulus, to break the modular symmetry group. Okay, so in this way you get rid of some complication, which actually most of the complication coming from the flavon fields. You can think that you have one or a few moduli dictating your patterns. So the dream is that this would naturally lead to the hierarchies, the mixing, and the CP violation we observe in nature. This is a very generic introduction. So of course I want to tell you how this works and how this modular symmetry arises. This, from the top down, if you want, could be this tau, this scalar, could be describing a toroidal compactification of extra dimensions. But you don't need really to worry about that when you are working from the bottom up. Still, the point is that different compactifications with different values of tau describe different compactifications, unless they are related by some special relation. You see, if tau prime and tau are related by this so-called fractional linear transformation, where A, B, C, and D are integers, and obey this relation down in the bottom, you may think you are describing two different things, two different tori, but you're actually describing exactly the same torus. So there is a redundancy in the description. This is a kind of gauge symmetry, actually. Not a traditional one, but in the sense of a redundancy in the description. And the set of all these transformations, so the set of these matrices A, B, C, D, makes up the modular group. It's the group of these 2 by 2 matrices which act on tau in this way. So they take tau to A tau plus B over C tau plus D. And your theory should be invariant under their action, the action of these transformations. You can present this group in terms of these generators S, T, and R, where they act on the modulus in this way. So S is the generator which takes tau into -1 over tau. It's an inversion. T takes tau into tau plus 1. It's a translation. And R is redundant because it doesn't change tau, but it can act on the fields. Okay, so we keep it. It's actually S squared. And I'm telling you a lot of things about this group, that this group acts on this tau. I also told you that as soon as this, this tau is enough to break the group. So as soon as it gets a VEV, your group is broken, right? But we are actually interested in seeing how fields transform, or how the usual fields transform, and then on building our Yukawas, which will be, we hope, constrained by this symmetry. So how do the fields transform in this setup? They actually transform in a way very similar to the traditional rotation. So this rho is a unitary rotation, but they have this extra automorphy factor, which depends on tau. This so the field psi transforms into a rotated version rho times psi in flavor space. And there is this extra automorphy factor, which depends on tau. And of course, C and D are defined by the transformation, and kappa is the weight of this field. Okay, so it's another charge, if you want. The field is defined by this charge kappa and by this rho, which will be a representation of the modular group. So we are very close to the traditional scenario where fields are rotated by unitary matrices. There's just this new factor. And let me comment briefly that these rotations, since the modular group is actually infinite, they will need to be blind to a large part of it. So this row will be blind to a so-called principal congruence subgroup. So it's an infinite subgroup of the infinite modular group, such that effectively this row is a representation of a quotient. Okay, so I will spare you the details. There is this infinite part of the group, and the row is blind to it. So essentially it's representing the quotient, which is a finite group. It's what we call the finite modular group, and it is actually nice that these guys are isomorphic to things we already know. Okay, so the field up to this factor transforms under a representation of this finite group, and if we put in different values of this n, we find, depending on whether we keep or not the R generator, we find the usual groups we know from traditional flavor symmetry model building: S3, A4, S4, A5, or their double covers, T prime, S4 prime, A5 prime. Essentially, what we did is to add this this constraint to the presentation, and we have made the group finite. I don't want to bore you with the group theory details. I just want to flash that the groups that determine the transformations are groups that we know. They have been studied, so this is also a flash of many references where these groups were studied for the first time. And because by now there are so many papers that I can only flash a bit of literature. For instance, there has been a lot of model building in the literature. Either you build finite model groups increasing this n here, so you go beyond A5. You can also combine them with guts. You can extend, not just one modulus, but more than one modulus, and this I will touch at the end of the presentation. Inflation, connection with CP symmetry, and so on. So rather than focus too much on what has been done, I want to give you really a flavor of how it works. Again, this is how the fields transform. And in a supersymmetric setup of rigid supersymmetry, we have a superpotential, which is basically, let's say, for Yukawas, you have two fields here and then the Higgs superfield also. You want to make it invariant. How can we combine fields to make something invariant in this kind of products? Well, we need to get rid of this automorphic factor c tau plus d to the power minus k. So either you trivially combine fields whose exponents cancel, or you do something a bit more generic, which is to include some function of tau, because this can also help you. If this function of tau transforms in this way, you are set, no? Because if you know how tau transforms, so if you can find a function of tau which transforms in this way, like the fields, you can, provided you can tensor out a singlet and the exponents all cancel, you can make something which is invariant. And so you have your superpotential, your Yukawas, your theory. These functions exist actually, and they are called modular forms. So they are, this is where holomorphicity and SUSY enter. If you could allow for a function of tau and its conjugate, you would have no predictivity. You would have like, you would have essentially infinite things you could write here. But if you are in a SUSY setup where you can only depend on tau and not its conjugate, there is only a finitely there is only a finite number of these modular forms for a given ky. Okay, so this is where the predictivity of the setup arises. Let me flash that for different groups we find, for instance, for, okay, this is a busy slide, but let's say you consider group A4 prime, then essentially at kappa y equals 1, you have only a doublet. So you have two modular forms, and that's it. Or for A4, so n equals 3, you have just a triplet, and at weight 2. So this is why the setup is predictive. In fact, let me be a bit more explicit. Let me just show you, if you wanted to build a random mass term of using two fields, just one field n with itself, and you are assuming invariance under the modular A4, assume that this n is a triplet of right-handed neutrinos with a weight 1, then you want to build something invariant. So the only thing you can do here, because the weights of the fields will not cancel, you need the modular form. You need this function of tau, which, as I shown in the previous slide, there is only one of this kind, a triplet. And so you, this is a well-known function which you plug in. Your mass matrix will have a form which is, in this example, very, very constrained, because it's given essentially by group theory and these functions. So you see that the only free coefficient is this overall lambda, because all the coefficients within this matrix are determined by the contractions, the Clebsch-Gordons here. These functions, as I told you, if you peek under the hood, you will see that they are functions which have some particular properties. They can be expanded as a Fourier series in this term Q of tau. But the point really that I want to show you is that really this, with a few assumptions, you can basically build a mass matrix which depends on a few parameters. So to give you something more realistic, we can look at models that have been done in the literature. There is this example that I usually show of a lepton model based on S4 modular symmetry. So you assume invariance under the S4 modular symmetry. You have your field content, which we take to be right-handed neutrino superfields, a triplet, a different kind of triplet of S4 for the lepton doublets, and the lepton singlets will be in singlets of the modular group. The second thing is the weight of each field, the kappa, basically that exponent, and then you can build your superpotential, where each of these terms will be a contraction, just like I've shown in the previous slide. So if I again peek under the hood, each of these terms will be given by Clebsch-Gordons and the known functions. Okay, so this is exactly the expansion of these terms. And in blue you see the free things that you will have to fit. So we fit varying these things, these couplings and tau. And here the G prime is actually the only physical phase in the model. Apart from tau, we can do even further if we impose CP symmetry, and then G prime is real and tau is the only source of CP violation. So this tau again is a complex field whose VEV can be the only source of CP violation in your model. This example is shown because it's something that actually fits neutrino data and gives some predictions. Okay, so these correlations, if you would like, essentially show how constraining the model is on your parameters, on your observables. With 7 parameters, you describe 12 observables in the neutrino sector. You have some prediction for the scale of neutrinos double beta decay, for the octant of theta 2-3, for the CP violation phases, and so on. Because essentially you fix the matrix, the mass matrix. You can even go towards even more minimal models with one less parameter. There was this model here. But the point is that these things are testable. You can rule them out in principle also with Juno. If you increase your precision in theta sine squared theta 1,2, you can see if this model survives and if it's consistent with all the data. Now, a technical point is that we will fit this by varying tau, and I will show you that we can essentially scan a restricted area of our of the VEV of this tau. But I don't know if there are some questions so far because I've been advancing quite rapidly. So regarding the modular setup, are there any questions or comments? So
Joe,
if
can you please
yeah.
connect these neutrino masses 80? Is it possible to reduce in that model that sum of neutrino masses, for example, to put it below 70 milli-electron volts in the model?
This is a good question because of the strong constraints, right, from cosmology.
Exactly, there was figure of 2024, I think, where they put, I don't remember my memory, but something around 70 milli-electron volts, 70 something.
Exactly. So off the top of my head, I don't remember because for some reason this is a reduced version, so it's not showing the full plots. I know that I will show you a model where this is where we have a fit compatible also with stronger bounds on the sum of neutrino masses. So if I'm just checking the paper very briefly to see the plot that is hidden underneath, just to confirm with you.
The result that you present should be normal hierarchy. For what about scenarios inverted hierarchy is ruled out, or there is also a parameter space to fit inverted hierarchy?
So in this model, we can only fit a normal hierarchy, while if you let go of the CP imposition, you could also fit inverted hierarchy. In fact, we started without imposing CP. We found, this is the first paper, 1811. We found several fits, but then we imposed CP and only one model survived, which is the one I'm showing. As I'm seeing here, it, however, is not, the sum of neutrino masses, the lowest value I can get is so it's 77 milli-electron volts. 0.077, so it's not so compatible with the new bound. Yeah. So,
this is imposing CP symmetry. I mean, you impose CP symmetry, it will get more restricted, I suppose.
Yes, this is imposing. So if you lift, if you don't impose, you get more less restrictive fits. You can fit in different regions, so more than one prediction, including inverted ordering. Yeah, thank you for the question.
Yes.
Okay, so let me now tell you a bit more about this, how this symmetry breaking happens. Let's say the details of this symmetry breaking and why do we care about this? Because the point is that we do not need to fit our model. When we try to fit our model, we don't need to search the full fundamental plane. In the sense, we don't need to search all possible scalars with positive imaginary parts. We can just look at this fundamental domain, which is, sorry, I had something else open and now I'm back. So the point is, we scan the VEV of tau. We don't have a mechanism to stabilize tau that is universally accepted, but this VEV will be stabilized somewhere in the upper half plane. And what I want to say is that we only need to scan this blue region because it's any tau which is inside this fundamental domain is equivalent to a tau outside. So it's enough to scan this, and we will, this is important because we will look into it shortly. But let me comment on CP symmetry first. So CP, as we've just discussed, can be combined with the modular symmetry. This is what we just considered. Essentially, you get real Klebsch-Schwarz coefficients in an appropriate basis. You also get a real coefficients in your mass matrix. So I won't go too much into that. I just want to say that if tau is the only source of CP violation, you have to be careful, because there are some values of tau which will still preserve the CP symmetry. So any value of tau will break the modular symmetry. Most values of tau will break the CP symmetry, except if tau is on one of these green lines. So if tau is on one of these green lines, you have no way to violate CP in your model. There's always an admissible CP transformation. Okay. Other important points in this fundamental domain are the ones shown here. This I, this omega, which is exponential to pi I over 3, and I infinity, which essentially corresponds to very large imaginary part of tau. So if you stabilize tau at one of these three values, not only do you conserve CP because you are in one of these lines, but you will also conserve some symmetry, which is a residual modular symmetry. And this is a strange group, the modular group, because it's non-linearly realized. It's a generic value of this scalar will break it, but you can still preserve a Z3, a Z2, or a Zn, depending on where your tau sits. If it sits at omega, you have built-in a Z3 symmetry. So I looked actually at a paper from your group recently, the one with the radiatively generated masses, and I was wondering, because if tau is equal to this omega, you have this Z3 symmetry which is preserved. So somehow, since you need a Z3, I was wondering, but I'm just thinking out loud, because this Z3 is there automatically. It's not something you add, it's part of a little part of the model group which is not broken. Okay. Anyway, if you sit at one of these 3 points, not only you conserve CP, you conserve this Z symmetry, and so some couplings will vanish. Actually, this is a key idea for texture zeros or for hierarchies, because if you are sitting at one of these points, tau is a symmetric tau, you could have many zeros in your mass matrix. And this is already very close to what we know for a hierarchical spectrum of fermions. If you deviate slightly from this symmetric point, your zeros will be lifted. So this is the mechanism that we recently called modular proximity-induced hierarchies. Some people call it criticality in this modular context, where you can have a small departure from a symmetric point, giving you a small parameter epsilon, and thus with group theory controlling the picture, a lifting of zeros that can give you a hierarchical mass matrix. I don't want to give you too many details. I just want to say that for the groups that we have seen so far, basically you can go up to epsilon or epsilon squared if you are close to y or omega, or even epsilon to the n if you are close to y infinity. So if your tau has a very large imaginary part. I just want to, it's maybe better if I just show you an example. So if you have psi and psi c, which are triplets of this modular A5 group, you can find that the group theory determines a decomposition under the Z5 that you are almost preserving, and then the structure of the mass matrix will be something like this. Okay, so you lift those zeros, and in an appropriate basis, you will have something which looks like this, which could give you a hierarchical fermion spectrum if enough forms contribute to the mass matrix. So this is a particular example which, I mean, this 1 epsilon to the 4, the coefficients here are determined by 1 or 2 parameters and group theory, Clebsch-Gordon. So it's not a Frogat-Nielsen in the sense that each of these elements has an order 1 constant which is independent. No, it's a scenario where these coefficients are determined by group theory and 1 or 2 few superpotential parameters. Actually, we are working on something which maybe comes out next month, which is what if there is only one overall parameter and thus the whole structure is determined by the group theory. So this is an interesting possibility, let's say an improved version of Frogat-Nielsen. So this is a small parameter, is very useful. And wait a moment, a small parameter can also be useful to do what I've discussed before, the symmetry protected seesaw. So taking something which is approximately L conserved and using this epsilon, which will be in our scenario some deviation from a symmetric point, that will lift L symmetric 6x6 Marana mass matrix to something which is phenomenologically viable. Okay, so how can we realize something like this with the modular symmetry? First of all, we insist on having triplets. This is a technical point because you really want to interpret hierarchies reliably, not coming from maybe tunable coefficients in your superpotential, but really from this epsilon. Okay, we can discuss further if you like, but the most important things is that you have a group assignments and charges that will lead you to this kind of structure in this lower right block, either with 2 or 3 right-handed neutrinos in the limit of epsilon goes to 0, in the L conserving limit. And also in the Dirac part, you need this structure which aligns correctly to have something that can give you lepton number conservation in the symmetric limit. So long story short, if tau is one of the symmetric values, you have lepton number conservation. We want tau close to this so that you not only get neutrino masses, but also the charged lepton masses, which are hierarchical from the mechanism we discussed just 3 slides ago. We want everything. We want charged lepton mass hierarchies and neutrino masses in a low-scale seesaw using the same parameter epsilon. So we did this. I'm not going to show you long tables. There is a landscape of models that maybe do this. We scanned few of them. We saw that not all of these can accommodate the data. The most promising ones were based on A4, T prime, S4 prime, and the points that were of interest were tau close to the omega, that corner there in the fundamental domain, or tau with large imaginary parts. And then, of course, the splitting of the pseudo-Dirac pair will depend on the model. So let me show you a few benchmarks. Actually, I will focus on benchmark B, where you see here, these are the E-reps and charges of the fields. So benchmark B is based on the modular A4 group. Our value of the modulus VEV is close to a exponential of 2 pi I over 3, this omega. And in this model, we expect that the pseudo-Dirac pair is split proportionally to the mass of the heavy neutral leptons themselves times this epsilon. If you work out the mass matrices, you will find this mass matrix structure for the charged leptons, and basically the same structure for the Dirac neutrino part, whereas you have this structure which is familiar from the first example I've shown you for the Marana mass matrix. And we have, if you go to appropriate bases, we will have this structure which shows exactly that we have hierarchical charged leptons and the structures that we need for the symmetry protected seesaw. We have 8-dimensional parameters in the model. We will have
Joe, sorry for interrupting, but we stopped seeing your presentation.
Oh, so let me show it again. Can you hear me?
We can hear you, yes,
Okay.
but we don't see your presentation.
For
Maybe
some reason,
you stop sharing the screen.
It crashed.
I think so. I think one of your account. Now I'm going to admit. Yes, I think you were having some connection issue.
Thank you. Thank you.
You're welcome.
Sorry about that. Let me allow it again. Can you see it?
Yes,
Yes.
now.
Oh, very good. So I don't want to bother you with details. I was just showing how the structure in the appropriate basis is the one we want. And okay, this is how to show it exactly. See, if epsilon goes to 0, you get the symmetry protected form. Also, these are the analytical expressions for the masses of the charged leptons, and you get them to be proportional to 1 epsilon epsilon squared. Okay, so we actually fit all the 4 benchmarks in different regions of this fundamental domain. These are C and D. C fits inverted ordering, D fits normal ordering. I was showing B, which fits in a region very close to A, and essentially I'm zooming in on the corner here as promised. We are fitting close to this omega.
Excuse me,
yes.
Joao.
Please.
Well, I have a doubt here, because how can you define a neighborhood that that accommodate to the data, or you just put and whatever value it is, and you can find some points that can fit the data?
Yes, we typically do 2 things. First, we typically scan the whole fundamental domain.
Okay.
Because you can find the generic fits outside of the region that you intend. Yes. Since here we are really desiring this structure, then we put a cut. So basically scan around omega, not too close, relatively large region, but then you are driven by the fits, by the minimization towards this region. But
Okay.
It's true. I mean, if you let your superpotential parameters, this G1, G2, G3, and so on, vary in large ranges, let's say 10 to the minus 3, 10 to the 3, then you are not doing hierarchies based only on a small parameter epsilon. You are introducing other hierarchical parameters, and then you can fit easily in other regions of this. I mean, typically, okay, it's not automatic.
Okay.
It will depend on this model structure. Did I answer your question?
Yes. So, well, to summarize, okay, there is no such a rule to find this point. Just we can prove points in the neighborhood and see if we can fit the data. Am I right?
Yes, yes,
Okay.
and of course
Yes,
there are
because
some. Yes, please.
no, because it will vary of the well, I mean, it will vary this point depend of the modular symmetry. Okay, so I was wondering if there's a rule to find some this point, but okay, then I guess that
Yeah, these symmetric points are the same
well,
for
I guess
any.
this point we can find this point, for example, this omega, we can find this point in for each symmetry, so we can find points in the neighborhood of these omega points. I mean, that am I right? Okay. But the neighborhood of this point, there's not such a rule to find, for example, I don't know, in the neighborhood, let's say for a circle of a radius r, I mean, that is not a rule for each symmetry. So we can find in the neighborhood some point between, let's say, minor or equal some r that we can find. Okay. Am
Yeah,
I right?
it really depends on the model and how large you want the constants to go. Because if you
Okay.
fix constants of order 1, then
Yes.
you will, for instance, if you see model C will not fit down here, because
Okay.
C is a model which works with the epsilon, the small thing that you have at your disposal, is basically small because the imaginary part of tau is large. And if all the rest is order 1, you cannot fit model C down near omega. You need to go to large imaginary part of tau.
Okay, I get it.
And the opposite for these models, right? Because if the rest of the parameters are order 1 and you want some hierarchy, it can only come from epsilon. So it can only come from being close to omega, and not the models are built such that you will reproduce every structure that you want, namely this one, due to this proximity. So A and B will not work up here, and C and D will not work down here, unless you allow for models for parameters which are very large or very small, but then you are going against the point of having an explanation for the hierarchies, right?
Okay, okay, thanks.
No problem. So let me just flash some curious things that we can find for model C and D. For these benchmarks, we find some parameter correlations, sorry, some observables actually, that are correlated. For the other models, we don't find these correlations. And as promised, Antonio, this model D can fit even below 0.067. So it's something which is acceptable from the point of view of the latest cosmological data. Also, let me flash some predictions of these 4 benchmarks. I hear this table. I just want to focus on the fact that for the normal ordering, you are above the very late future milli-electron volts threshold, let's say. And an important thing here is actually that CP is basically conserved. So even though we are not at the symmetric points, we are close enough that CP is minimally violated. This is something that is okay for the lepton sector because we don't know these phases, but could be a problem, as we'll see, for the quark sector. And to close this section and on how modular can do a modular-protected seesaw, let me show you also something about the heavy neutral lepton phenomenology, because I've been trying to sell you this model, saying that we now have light states that can be accessible at the collider. So what is the phenomenology that we can see here? And for these 4 benchmarks, actually in this flavor triangle of couplings between the HNL and the usual leptons, we actually have very precise predictions for benchmarks A, B, and C, which are the stars. Okay, and also some regions here, the star is the best fit. The shaded regions are the regions that you expect to be accessible for normal ordering to right-handed neutrinos or inverted ordering, but we only occupy a small portion of these regions, except in model D, where we have 3 right-handed neutrinos, and we can be a bit more. We find fits in these regions in a larger region. Still, it's a constrained region, so the coupling to muons is rather small in this model. And in terms of the mass, of course, we don't have a constraint on the mass of the HNL, but if we vary it, we see, as I promised, that it's we have couplings which are above the seesaw limit, because the neutrino masses are not small just because of the seesaw formula, but also because of this epsilon. So epsilon lifts us from the seesaw limit and puts these benchmarks in the range for some masses, some values of the masses of the new states, in the range of future experiments that will probe this parameter space. So this is for model C, which has even larger couplings, and model D. This depends on the flavor structure, so these are approximate constraints, but you see how in different scenarios they can be tested in the future. Okay, so this is how this epsilon can be there to give us hierarchies and give us symmetry protected seesaw where the lepton number is broken by the same small amount. So there is a connection between charged lepton masses and lepton number breaking. But as I told you, there are things that motivate us to look beyond this scenario. As we've seen, we are doing something where we start from a small symmetry breaking sector and derive the symmetry group. This was the fact where you have one modulus, a symmetry breaking sector, and we've just seen how this is compatible with S3, A4, S4. However, there is a motivation to go beyond just one modulus, just a simple symmetry breaking sector, which is one modulus based on genus 1 associated with a torus. and go beyond to genus 2, which involves more moduli. And this is exactly what I've shown you, that if all CP violation arises from the symmetry breaking sector, so from the moduli, then we are in trouble if we want to do quarks, no? Because hierarchies, by this mechanism of being close to a symmetric point, but also CP violation, I mean, it's tough. In fact, there was a study we did for quarks 2 years ago where we tried to fit, and we saw it was incredibly difficult to do it using the mechanism I've just explained of modular proximity induced hierarchies. To reach the viable region, we would need to be too far away from the omega. There was a recent paper by Ivo Varzelas and his collaborator who showed that if you allow for a mixed origin of these hierarchies, you could do it. Actually, they do it close to I, but to do it with a single mechanism led us to consider something which has been studied also by other groups. So to go beyond the genus 1 setup with 1 tau to something which is genus 2. So this has been studied by several authors before, actually 4 or 5 years ago, some of these papers. And the point is that instead of looking at the modular groups, so I'm putting here a little 1 subscript because it's just to show that it's genus 1, but this is what we've just seen, no? We've just seen this is the modular group. In genus 2, we are going to consider the symplectic group, which is this gamma 2. It's the generalization at genus 2. And the transformations are not 2 by 2 matrices of integers A, B, C, and D. They are 4 by 4 matrices, which, okay, preserve the symplectic form. These are details that I won't bother you with. I just want to do a side-by-side comparison. So you could generate these matrices with this S and T, and R is the S squared. To generate these 4 by 4 matrices, you need 4 generators, S and T1, 2, and 3, where this is not just the identity, but is basically one of these 3 symmetric matrices. The point is you have 4 by 4 matrices, and you are not working just with one modulus. You, with as imaginary part positive, as we've seen transforming like this, you are working with several moduli, which in this case arrange into a 2 by 2 matrix, symmetric. So you are working with 3 moduli, tau 1, tau 2, and tau 3, which have to obey basically some conditions on the determinant and trace of this imaginary, of the imaginary part of this matrix must be positive, okay? And the transformation is generalized to this. So now this is not just a quotient, it's really a matrix, an inverse matrix, where A, B, C, D capital are these ones defining the transformation. Okay, and of course we care about fields and flavor, and I've just shown you that fields transform like this in the modular setup. This row was a representation of a finite modular group. Again, here I'm putting the little ones of these groups, which were S3, A4, and S4 and double covers. What happens for higher genus? We get something similar. So the field transforms with C tau plus D determinant of this matrix now, but it's very similar. So you could also do some quotient of something similar, principal subgroup, and you will get a finite group. First obstacle in this program was noted by Ferullo, Ding, and Liu, was, however, that these groups that you start obtaining for n equal 2, 3, and so on are very tough groups. So you have S6, which is a group, rather large group of order 720, which has no doublets or triplets. And if you go to this next group, which is the Burckhardt group, when n is 3, this is a group of order 50,000 something, if I'm not mistaken, and again, no doublets or triplets for this group. So the idea of these authors was, okay, let's pause here. We want to do flavor. So if we could somehow restrict our tau not to be, sorry, this matrix, generic matrix tau1, tau3, symmetric tau2, but maybe some constraint on this matrix, maybe we could do something which is worth it for flavor. So in the space of the three taus, these three complex fields now, maybe we would be not in this general three-dimensional, three-complex dimensional space, but maybe be constrained to some surface, some region within it, okay? So suppose you live not in the full space, but on a region, and they considered some special regions which, if you take a point of this region, you'll collect all the elements that, all transformations that will leave it invariant. You are defining the stabilizer associated to these points. They discussed the normalizer, which is something else. It's the set of transformations which instead keep you inside the region. Okay, so I just present the stabilizer because the normalizer is defined from it. Okay, and the point is, instead of the full space and every genus 2 modular transformation, why not restrict ourselves to a region, sigma, and the set of transformations within the normalizer of this region, such that you will never leave this region. So you can consistently stay within these so-called invariant or fixed regions. For the genus 1, actually the 3 points that we see, the 3 special points, omega I and I infinity, were the invariant regions that you could have. Here the structure will be richer. I will show you in a second. But okay, so if instead of using these horrible groups, we restrict ourselves to transformations of the normalizer and to a space which is this region sigma, a subspace, then you can quotient out and you can have a final group which is manageable. Okay, so either you have something which is S4 cross Z2, which has triplets, or something which is S3 cross S3 semi-cross Z2, which has doublets, and you can use these to build flavor models. This is what was done in this paper by Ding, Fermion, and Zhu. And we also looked into this, particularly because we were interested in hierarchies, right? So we wanted to be, actually this other paper from 2 years ago, they considered also something similar, but not for hierarchies of charged fermions. We will see in a moment. What I want to show is that these are the regions that you can have at genus 2. So the special region sigma, where instead of taking a generic 2x2 matrix tau1, tau2, and tau3, let's say you put tau3 to 0, then you are on this two-dimensional surface we call T1, or tau1 is equal to tau2, and then you are on another surface, tau1, tau1, tau3, tau3. Or you constrain it even further, and there is just one dimensional left, which is, let's say, tau2, and tau1 is fixed to I, tau3 is fixed to 0. Okay, so you have all these points or regions that you can use. I see that we are running out of time, so I will just briefly sketch the idea. I mean, these regions were known for a long time. The groups that you have at your disposal to do flavor were also known. You can see these papers here. What I want to show is that suppose you are inside a region like a two-dimensional region where you have tau1 and tau2 free. Then inside this region, you can even go to a sub-region, which is a line or a point. So some of these regions, which are lines or points, are inside each other. If you are, let's say, in this region where tau3 is 0, you can further reach a point, let's say this omega I, which is inside this region. And actually, we want to be not at this point, but close to this point. So we will have some epsilons at play. These epsilons will basically define the distance within this special region defining our flavor to the more special region of enhanced symmetry. Okay, so as I told you, this paper, they considered the neutrino sector, and they considered several trajectories going from this subspace tau1 equal tau2. We focused on this subspace where tau3 is 0, which is similar to a product of two tori, but not quite, because there is some swapping of tori still there. And we basically explored all the possible trajectories, all the possible approximations you could do within this space to even more special points. So just to flash the results, we found in this table, I'm hiding a bit of things that are not important. We found that if within this space you approximate, let's say tau1 approximates omega and tau2 is free, then you have something which is very similar to genus 1. No, you have the possibility to have matrix elements which are order 1, order epsilon, epsilon squared. This is not new in a sense. However, if tau2 also approximates another value, let's say I or omega, you can do something with these. I mean, you're not at these points, you are close, and with these proximities, you can do some hierarchies, some which go all the way up to epsilon to the cube in this case, or even epsilon to the 7 in the case where your tau1 and tau2 are both near omega. And so your full matrix is near here. And things are even more complicated if you are near II, but the point is you can go up to epsilon to the 4 in this kind of scenarios. So you have some more freedom. And we've illustrated this with some benchmark models. Actually, so the flavor group is, as I told you before, this S3 cross S3 semi-cross theta 2. We found a model which actually, okay, I will not bore you with the details. These are the charge and assignments. These are the matrices that you predict. It's not a very predictive model. It's just here to show that you can do this program. And it's interesting because we, as I was saying, I think to Nicholas before, the model can fit in different regions. So if you don't impose anything, we find that you can fit in 3 different regions. We can find a fit where tau1 is close to omega, but tau2 is not close to anything in particular. And then if you go to appropriate bases, you will see that your UCAL matrices of up and down will have something like this shape. So the spectra is something like this, 1 epsilon epsilon square. But we also find a fit in another region where both tau1 and tau2 are very close to omega. And here the structure is different, but actually very similar. You just replace epsilon by its square. So spectra of the type 1 epsilon square epsilon 4, or even we find the fits where tau1 is close to omega, but tau2 is close to I. So in this vicinity, you can do something where ups and downs have different asymptotic structures, and downs are the first 2 generations are very close in scale. You need to play with the coefficients to do this splitting of generations, and its hierarchy is different from the one in the up sector, but it's something that can fit the data. So I flash as a final slide before concluding the values of things. So the epsilons that we find are order 0.02. So this is the 3 different fits that we find. And the point is that we can do something which is only violating CP from the value of taus, but still will fit this perfectly fits, essentially fits the quark data at high scale, so it fits the CP violation in the CKM matrix. Some tuning still appears when you do these fits. There is some hierarchies between the superpotential couplers. I mean, nothing dramatically like you have maybe something which is order 100 here in this model, but typically not something dramatic, because we find that even though you explain the hierarchies in masses and you can fit CP violation, you have to tune things a bit to fit the mixing angles. For instance, in this model, the first column, this value of epsilon will also naively be the Cabibbo angle. You see it's too small, so if eventually all these parameters here will need to conspire to produce a CKM which is acceptable from the point of view of the Cabibbo angle. This kind of tuning is what I mean when I say we need to fit the mixing angles. Okay, so let me summarize, because now I tried to finish early and I'm finishing a bit late. I tried to convince you, or if you already are familiar with the setup, to show a bit that modular symmetries can be predictive in principle. They could provide an origin for CP violation from the symmetry breaking sector alone, while explaining fermion mass hierarchies, maybe also participating in the seesaw explanation of neutrino masses, while producing intensity frontier testable heavy neutral lepton signatures. This was the symmetry-protected seesaw where we exploited this epsilon, and I tried to show that maybe we need to explore beyond genus 1 to understand also CP violation in the quark sector if we want some unified framework. So thank you for your time and attention, and please let me know if you have any questions.
Thank you so much, Joao, for the very nice and very complete tone. Question from the audience? Any questions? Joao, in some part of your presentation, you were mentioning in the different classification of the models, the A4 prime and S4, where the model were working properly when considering only one modular flavor symmetry in the vicinity of the fixed points. How to differentiate, for example, between these two models? I mean, if you build some specific models, which of these models will give you more, will have a better fit to the data, better fit and more predictive?
Yes, I can tell you that these three special points are there for independently. I mean, Z3 and Z2 are there independently of the finite modular group, whereas Zn is there. This n depends exactly on that finite group, and so there is already there. If you are close to this Zn, you are already being sensitive to different group structures. But it's really there is a wide possibility. So it depends on what you want to do. If you want to use only one parameter, maybe you cannot do it with these small groups. If you want to do something of this kind, where you also constrain the neutrino mass matrix, then you scan things and you find that if you want something predictive, you will exclude A5, you will exclude S3, simply because you cannot, in those groups, find, I mean, you can demonstrate that you cannot find these structures, okay, in the symmetric limits. So epsilon goes to 0, you will find these structures only for some groups and some charge configurations. So what I want to say is that to select a group, you can play with many, but to select a group, you have to do a mix of these considerations. What do I want to explain, and what constraints it will do for the representations, and something which is less theoretical and more phenomenological, which is to play with several groups, try to fit and see if you can reduce the number of parameters. So there are these two approaches. No, try it. Really, you need to decide what you want to prioritize. If you want to prioritize small parameters, explanation of hierarchies, seesaw structure, CP violation. Yeah, but yeah, there is not a group that I would say is better than the other.
Understand? Yes. In your, you were considering, you were showing prediction for this pseudo-Dirac lepton mass for A4 prime and S4 prime, which one is more suppressive than the other. One goes with epsilon and the other with epsilon squared. I think the slide below, before, two slides before, above. Yes, so, no, you analyze it, for example,
because there is a slight delay.
Yes, the other one. Yes, this one, exactly. Do you analyze leptogenesis? Because maybe from leptogenesis you could get another way to differentiate among the models, because given that they give you different prediction, it seems that S4 prime tend to favor a more neatly degenerate pseudo-Dirac lepton mass. Maybe they will have some implication and different prediction for resonant leptogenesis.
Yes, so we speculated about this and we were working on this, but the problem is that to do it correctly, you need, because this is all supersymmetric, to do it correctly, you need to consider the two Higgs doublets that are in play in the resonant scenarios. As far as I know, there is not a clean template for this, so it's not obvious. At the time, I think we searched, but even if you decouple the SUSY partners to keep the Higgses, the two Higgs doublet model, we cannot go beyond some rough estimates. I don't know if you know some better works on this. So two Higgs doublet model, basically of the type that is compatible with SUSY. I think it's type 1, if I'm not mistaken.
Yes, if you have two Higgs doublet, you can have contribution due to scalar exchange in these washout processes. But usually, as far as I remember from other works, that the contribution for scalars tend to give a subleading contribution in these washout scattering processes that wash out the lepton asymmetry. But the main contribution, I think, will come from interference between tree-level and one-level diagram. But if you have the scalar, they may enter indirectly in the loop. You can have contribution.
We have tree-level because so we have where do I have that? Okay, let me just.
No, yes, tree-level for neutrino masses, but I was thinking in the interference between considering the decay of the lightest pseudo-Dirac leptons into, for example, neutrino and Higgs, or in your supersymmetric model, it will be also in the charged-lepton and charged Higgses from HU, exactly from this Dirac pair. So you may have the tree-level diagram, and also one level contribution arising from self-energy and this vertex correction. And the interference between tree-level and radiative correction will give you lepton asymmetry. And there should be some correlation between this lepton asymmetry and the mass splitting of the pseudo-Dirac lepton pair. So maybe through leptogenesis, you could have some way to differentiate prediction between F4 prime and the A4 model that you were showing in some of your slides, because one gives you epsilon and the other epsilon squared.
I fully agree. I fully agree. I think at the time we wanted to put the idea out, so since we could not have we could not do it consistently, the full leptogenesis picture, but I think this is something worthwhile pursuing, yes, because it will be a discriminant, as you say. Yeah, thank you.
Thank you, Joao. More questions from the audience? Questions? Joao, I want to make a comment. Yes? When you were mentioning about this radiative model with S4 prime symmetry, that one of my collaborators put it in the article that I am work with other collaborators. Yes, we impose this C3 symmetry because here our philosophy in the other model was to have this radiating neutrino mass, and we want to forbid some three level and some one level contribution to acting neutrino masses, so we want to forbid the three level mass splitting between the CP and CPO neutral component of the inner scalar. So that's why we introduced the C3 symmetry independent of the S4. So this was we imposed by hand, but in our case it was broken. So it's a different than your C3 residual symmetry.
Yes, but I was wondering if you could, do you find a fit if you put tau exactly equal to omega? Because if you do, maybe you can find a cousin model, second model where this Z3 is not something that you need to add, but is there.
In our model, we get some prediction for the real and imaginary part, but I don't remember for this W, because this fit is, Jeremy did this fit, but for the W, I'm not sure if we had this, I mean, for exactly W, if we get some points.
Yes, it needs to be exactly, because only then do you have Z3, which you need right to be exact.
I think that no, but this yes, we have to tune a bit the real and imaginary part of tau, but I think for exactly W, I don't remember that.
So maybe you would need to do a different model. Yeah.
Yes, it's a different.
Yeah, I was just curious because it seemed to be a nice, and it would be nice if you did not have to put it extra. Right? If it was already there, it would be cool. That's just.
Yeah, but here the symmetry that is residual in our case is the in SA2 symmetry. I mean, from the breaking of the S4 prime, because we had this, we assign odd modular weight to the particle belonging to the dark sector, and the particle.
Yes, that is a different Z2. That sorry, it's all
exactly
in every
point.
One, yeah, it's another Z2 that is always there. Sorry. Yeah.
Exactly, it's another. So our philosophy is different than in your philosophy, because in philosophy or C3 we impose because we don't want we want to go beyond one loop level. So we want to forbid the phi daggerita square term. And then we need to impose the C3 symmetry and the C2, and there is a residual C2 symmetry for the radiative mechanism, but here it arises from the breaking S4, but through having odd modular weight to the field.
Exactly. That's very nice. I think it's also been used to stabilize dark matter in the past, and it's based on this R, right? Because you see, R squared is 1, so R generates that Z2, which doesn't change tau, so any value of tau will preserve it because it's invariant, and it can affect the fields in the way that you just described. It's very nice. It's always there. Yeah, it's this R.
Yes, it's redundant. Yes, I think so. Yes, it's related with the modular weights. In our case, we put it
exactly. So the only way that this symmetry can show is the weights. As you say, they are odd, and then there is no modular form that you can, because the forms are even. And in fact,
yes, we are not using a double covering group. We are using just S4.
So if you drop the R generator, you get just S4. And so the R, you cannot, you don't have the way to put the modular form of odd weights. And so you do what you are saying. It's very nice, yes.
Thank you. Thank you, Joao. We are going to have the next year a head conference. It will be nice if you can come. I think it will be something like the week of, I don't remember my memory, but something around the week of 18th of January, 17th of January, something like that.
Very early.
Conference.
Very nice. Yes, I have to see, because my situation, I mean, I just quit, my contract ended with INFN So I'm in limbo for the moment. But these works were done with them, and there is still something coming out right now. So if I can, I will make it. If I can make it, I will go.
It would be nice if you can come.
Thank you very much. Yeah, sorry, this was a bit scattered, but I think this is fascinating, even though it's not, it's still very speculative. We must keep it in mind.
Yes, I like this topic of modular symmetries. Very nice. Any more questions from the audience? If there are no more questions, we send you out for the very nice and very complete seminar. Thank you so much, Joao.
Thank you for your time.
Thanks a lot. Very, very nice seminar. Thanks a lot.
Thank you. See you.
See you soon. Hope to see you soon in the future. In some conference, on some visit.
Sure.
Have a nice time, all of you.
Bye. Bye.
Bye. Thanks a lot.
Bye.
Thank you for the
Bye.
talk. Bye.
Thanks a lot.
Thank you.
Bye.
Bye.